Are there any questions at all? I gave you a bunch of homework. Yes?
I had a question just about the powers of the book.
Yeah. Any problem you want?
There's an exercise in here that has just a voltage source. I think it's on page 204 of the book.
Okay.
So
Is it second or first?
the first one, D5.1.
All right. Here. He's talking about a drill prop, but you have a voltage source here, right?
Yes.
I think that, and then you have a resistor here. Is that right?
Yes.
And then it splits off into two a resistor and capacitor.
Yes.
All right. Now, give me the value of this resistor
That is 2 ohms.
and the value of this
Negative J4.
J4 ohms is the reactance in here.
4 ohms.
So that's 4 ohms. And then what the power through, by the way, the voltage source is,
That is 12 at angle 60 degrees.
well, the angle is not going to matter, but we can put 60 degrees in there for completeness. All right, here's the deal. He's asking about how do I get the power in this element and this element. By the way, how much average power is absorbed by this element? 0, right? Because it's a capacitor. That light's on. So if we're doing this problem, and you want the power in a resistor, if we're talking about peak current, the average power dissipated is going to be 1/2, right, times the value of the resistance times the magnitude of the peak current squared, right? Y'all with me on this one? This is standard 1/2 times R times the magnitude of the current. You can put an M here. I think some of you are used to seeing M as magnitude. It's the peak value. It's the coefficient of the cosine waveform. Now, when we do this to figure out the total current, first I'm going to find the total current here, all right? I'll just call it I total or I source, because this is the source. Well, to get that, what am I going to need? I need the total impedance of this, right? Y'all with me? So the total impedance of this, I'll call it Z total, that will be equal to this value 2 plus the parallel combination of these two, right? So you could say plus 4 minus J4, this times this over 4 minus J4. That's going to be the total impedance. You all agree with that? You asked me about this. You see what I'm doing here? Once I have this total impedance, and we'll put a number in a second, if I want that source current, the source current would be equal to 12 at an angle of 60 degrees over ZT here. Everybody agree with that? If I wanted that current, and I do, you all agree. Now your calculator should be able to do this rather quickly. I think they all can do this fairly quickly. First, you need a number for this, right? You can give it to me in a real and imaginary or polar, either one. Anybody give that to me now? Go get your calculators out, see if you can do it.
4 minus 2i.
4 minus what?
2i.
J.
J. Right.
All right, it's
Right.
4 minus J2. Anybody confirm or deny? Anybody at all?
Yes.
How many got that? Okay, I'm seeing hands. Okay, are we together on this? Yeah. Once I have that, I can take this and divide it into 12 and 60 degrees. Do you agree with me? What do you get then for this? And now I just want polar form. I want a magnitude of that current. I don't care about the angle. But I mean, you can give me the angle too. Magnitude. Please do it on your calculators. This is where you're going to learn to use it. I was told by Bobby Woodward that he's the vice president for student, I guess, activities on campus, that a lot of people went down to Florida games, like buses chartered and all sorts of stuff. Is anybody planning on going down? You guys, how many put them up again? Okay, then the rest left, probably.
We've already got 3 that said they've left already.
What's that?
We've got 3 people that said they already left.
Yeah, probably. Well, we got a football player in here, so he left. I don't know. Anyway, I'm just curious about that. I'm glad we're doing this video, though, because at least they can catch up if they miss it. So what do you get for this value? That's a good question.
2.68 at an angle of 86.565 degrees.
At an angle of what?
86.6 degrees.
Anybody else confirm that? Magnitude and angle. Make sure you can do it on your calculator class. Are with me? Now, once we have that, that's the current through this 2 ohm. But we need the current through this 4 ohm right here. Right? That's what I need, I4. So how am I going to get that? How would you get it? Anyone? This is a standard kind of problem, right? You've got the total current flowing into the parallel combination of 2 elements, right? How do we always get this? This is current division, don't we? So what does current division say? I4 is equal to the total current into them, I source, times the opposite impedance minus J4 over the sum of these two, which is going to be 4 minus J4. Y'all agree with me in class? Right? How many understand what I'm doing here with current division? Class, do you? Okay, important you have this down, it's very important. So what's this going to be? Use this value for IS, 2.68 at an angle of 86.6 degrees times that. Yeah. This is just equals. Here? Here? That's 2.68 at 86.6 degrees. I'll try to make it a little better. All right. So what do you get for this value? Give it to me in polar too, and then hopefully I'll answer any question you have after this.
I got 1.9 at an angle of 41.6 degrees.
1.9 at an angle of, say it again?
41.6 degrees.
How many got that? You got that? All right. Now, once we have the currents, we've got the average, we've got the power. All right? These are peak values of current. They are not RMS. If I wanted the RMS value, what do I have to do? One single thing. If you did the problems, remember. I take the peak value and divide by square root of 2, or multiply by 0.707. How many of you remember that from the lecture? Remember, you're going to be asked to do this stuff a lot. So you have to get familiar with peak versus RMS, root mean squared value. Now that we have this, what's the power going to be dissipated in the 2 ohm? If I just look here, what is it going to be? It's as easy as it seems. It's going to be, if I'm using peak values of current, it's what? 1/2 times the resistance, which is 2, times the current squared through it. Well, the current is this. It's 2.68 squared. That would be the power dissipated in the 2 ohm, and the power dissipated in the 4 ohm resistor there would be equal to 1/2, right, times the resistance, which is 4, times the current through it, which would be 1.9 squared. And you can give me these values. I have a comment here that's going to be important. What do you get for this one? Well, the 2's cancel, so it's 2.68 squared. 5 something, what is it?
7.18.
7.18? Sorry, 7.18 watts. And this one? 3.61 watts. Pardon me?
Alright, it was on 42.
Which one's wrong?
It should be 7.22.
7 point.
No, top one right, top one right. Sorry, bottom one.
This is what?
7.22.
Okay. Now, here's something I want you to hear me on. This is a mistake. And you know better than this, but it still happens. What people will do, where it says I squared, instead of putting the magnitude, what they'll put is a real part plus JB, and they'll square this. That is wrong. It's always the magnitude of the current squared. Magnitude would be A squared plus B squared square root. You square that, it's A squared plus B squared. Y'all hear me? So when you put in the value for current to square it, it's just the magnitude that gets squared. Don't put in a real and imaginary value and square it on your calculators, because it'll be the wrong answer. Unless you take the magnitude. I'm warning you. Yes, sir.
What are the subscripts?
These, that's just the value, that's 2 ohms and that's 4 ohms. I'm just trying to say that.
It's 2 ohm and 4 ohm, okay.
It's just the values. Now, I hope I answered your question. Would you give a specific on that?
One other thing I had was just, when I was doing this, on the previous page, they showed how to solve the problem. I basically did it the same way, and I wasn't getting those answers. So I didn't, is it just because of the current division?
Well, I don't know how you're doing it, but and I don't know what you're looking at there, but you always find the current through the element. If it's a resistor, that's what you're after. You're not, You can use the voltage across it, but you don't need it. What you really want is current through the resistor, square that value, multiply it by the resistance, divide by 2 if it's the peak value. If it's RMS, you just take the RMS value and square it times resistance. Okay.
So how was this, the IS value, why was that of the total circuit?
No, the current, what I'm looking, this is the current that's flowing through the 2 ohm, right? That current divides into these two things, right? But if I want that current, I find the total impedance divided into 12, don't I?
Because when it comes around on the other side, we'll pass through all those.
Yeah, it splits, right? It's current into is equal to current out of. So if that current's flowing here, it's also flowing through there, and it's flowing there. Right? That same current's flowing in every portion of that circuit. You all see this class? Any questions? It's not a bad one to talk about. You have another one?
There's another one, or the one directly below it. It has a resistor in parallel with the current source instead.
Doesn't matter. Maybe we can do that one too. Just tell me it's a current source?
Yeah, on the far left branch there's a resistor.
Oh, give me 1 second. Let me erase this. All right. Let's start with the source. You said it's a current source?
There's a current source in the middle that's 10 amps at angle 30 degrees. And then
Alright.
to the left of that is a resistor in parallel with it, that's 3 ohms.
3 ohms?
Yes. And then across the top to the right, there's a 4 ohm resistor.
Oh, here?
Yes, at the top.
Uh-huh.
And then down the right side, there's an inductor of J2 ohms.
All right. And they want to know the power dissipated by the 3 ohm and the power dissipated by the 4 ohm, right?
Yes.
All right, class, remember that what we're after is the currents through these things, right? Now hear me on this. Yes, miss? 30 degrees, sorry. All right, now just listen. If you get this, I mean, it should become so painfully obvious after this. Only thing I'm after is current, right? That's it. I've got the current here. Do you see that these 2 elements are in series? Does everybody see that? They're in series. Those 2 elements are in series and they're in parallel with this. You all see that? So if I want the current here, I can say it's the total current because 10 is going into this parallel combination of those, correct, class? I can say it's 10 times, if I want the current through here, it would be the opposite impedance over the opposite impedance plus that impedance, right? So if I want the current through the 3, and I'll just put it I3. I would say I3 is equal to the total current, 10 at an angle of 30 degrees, times the opposite impedance, which would be 4 plus J2 over 4 plus J2 plus 3. Does everybody follow me? Now I add them. That's current division. How many understand that? Have to know current division very, very well to do this course well. Remember, you're going to see this over and over again. Now that's going to be a magnitude at an angle, correct? I'll ask for it in a second. What about the current here that's flowing this way? Call it I4. Well, there's 2 ways to get it. You realize I could say I4 would be the total current times this, right? The opposite over the sum. Or I could just take 10 minus I3 and get it. Follow me? So I could say this is equal to 10 at an angle of 30 degrees. Make sure you do this with polar numbers too, by the way. So it's 10 at an angle of 30 degrees minus whatever I3 is. Has to be I4. Agreed? Y'all see what I'm doing here? Or I could say, just use current division here. I could say this will be equal to 10 at an angle of 30 degrees times, and then it would be the opposite, which is going to be 3, right, over the sum of 3 plus 4 plus J2. Either one gets me the results. What do you get for the current, the I3 value, class?
I get a 5.7 at angle 28 degrees.
28 degrees. And for I4? If you've got that, just take that, make it a negative and add it to 10 and 30. I think you can put polar numbers in and do additions with the most calculators fairly easily. But you have to be in Poland, remember that. Anybody? 4.3? Say it again?
4.3 at angle 32.
All right, now that I have that, what's the power through the 3 ohm gonna be? Class? What's the general form always, right? So it's gonna be 1/2 times 3 times the current through the 3, which is 5.7 squaring. That would be the power through the 3. And what would the power absorbed by the 4 ohm be? 1/2 times 4 times the current through the, which is 4.3 squared. Follow me? All right. What do you get for the power through the 3? 5.7 squared, 36, somewhere around 40, is that it?
48.735.
48.7
.7.
watts. What about here?
36.98.
Say again?
36.98.
Okay. So that's how you do that one. Yes, sir.
Those answers are different than in the book. Is there a reason why?
You got me. I mean, are these numbers right? Is this 3 ohms?
Yes.
Is this 4 ohms?
Yes. For four ohms, they're showing that it's 33.95, and then for 3 ohms, they're showing 56.
Wait a second. I think we found the problem. Go ahead.
Yeah, I switched it to 6.143.
Oh, I'm sorry. I3. Get the I3. Sorry, just write it down. Go ahead.
6.143, angle 40.662.
Just 40.6 degrees. What about this one? If that's wrong, if that was wrong, this is probably wrong too. But what did you get?
I got 4.12 with an angle of 14 degrees.
4.12, angle of 14 degrees. Anybody else get that?
Yeah, that's right.
All right, now I'm just.
It's my fault because I did 4 plus I instead of 4 plus 2 I. That's on me.
I was so confused.
All right,
The
but
first answer was
these are the
right.
right values,
And I
right?
was like, I'm not
Then
getting these calculations.
what are the
Like,
wattages?
dude, what's going on here?
That's 6.143 squared. You're gonna have to tell me what that is. And down here, it's 4.12. So these values should be right if we've done that. What do you get for this one? This should be the same as in the book if they have answers.
56.6.
56.6. And here,
33.95.
33 point what?
95.
All right, now, look, I want to just make sure you understand this. The power here is dissipated. It's turned into heat for all intents and purposes. Probably. The power here is dissipated. This doesn't dissipate anything at all. Right? There's no power loss there. All the power is supplied by this source, the 10 amp source. All the power is supplied by that. And there's a thing that I'm going to show you about where we actually start designating signs with power. Now, that comes a little later. But you'll see that the sum total of all the what's called complex power in the circuit from all the elements is 0. So a source actually has a, quote, negative power associated with it, and resistors have a positive power because they dissipate. Yeah.
Would the average power of the system just be those two heads?
Yep, that's it. And that's what he probably has, if he asks for total power. So, that's that one. Was there another question? Because I gave you quite a few problems,
33.95.
and I gave the solutions too. If not, any, yes, sir.
So, 5.1 and 5.2 were like similar problems, but 5.2 should be more.
Hold on, 5.1, I gotta take a look at the instruction sheet. 5.1, go ahead.
So they're like the same type of problem, the 5.2 is working significantly differently than 5.1 here.
I'm gonna put this down for everybody. You're gonna see, I promise you're gonna see how easy these are, all right? For
For the first
5.2,
one,
he
yeah,
has
I didn't
this.
do this one though.
He has a voltage here. V1 of 2. Then he has a resistance, 2 ohms. And he has an impedance minus J2. And it's a completed circuit, and the V of T he has here is 24. Now watch this. Here he has 24 cosine of 377T minus I'm sorry, plus 20 degrees. So that's this V of T. And he wants I of T. I'm going to show you how to do this quickly. That's what he's after, right? Listen, the way you do this, don't write differential equations. Don't do anything like that. Turn this thing into its equivalent phasor domain circuitry, all right? So if I have 24 with this argument, really, we suppress the omega here is 377. You all see that, class? That's radians per second. Everybody, it's the coefficient of T, correct? Inside the cosine argument. You all see this, everybody? If you do, let me see your hands to make sure. All right, gotta make sure you see that. I got omega. You suppress omega when you go to the phasor domain. Just magnitude 24 at angle. Now, it's 20 degrees. Right? That's volts. Do you all see that? Now, if I want the current, now listen, if I want the current here, I've got a voltage and I've got an impedance. If I want the phasor current, I'll call that phasor I. That's going to be equal to 24, that's the voltage at an angle of 20 degrees, right? Divided by the impedance, which is 2 minus J2. So give me that in polar form, then I'll take it back to the time domain. Whoever said that. What do you need in terms of magnitude?
8.48.
Say it again.
8.48 or 49.
8.48 at
65.
65 degrees, right? Now, hear me. That means in the time domain, the observable current, I of t, would be equal to 8.48. It's the magnitude of that, right? Then you would put the cosine of 377t, and you would add that phase angle plus 20 degrees. That would be the current. So now I've got the current at any element in the circuit, right? And what do they want now? Read that part. Because now we can get the average power dissipated if we wanted that, but go ahead.
I think it was the instantaneous power.
Supplied to each element?
Time.
What's that?
That's a function of time.
Instantaneous power is supplied by the source or by dissipated by an element? What does it say?
I think around the
As a function of time.
You want to know how much power is actually being dissipated in the circuit as a function of time. Go ahead.
It's saying find the equations for the current and instantaneous power as a function of time.
All right, then he's talking about the total power supplied to the circuit. Here's what you end up doing. We've got the current as functions of time, as a function of time. Correct, class? Power in general, P of T, instantaneous power, is equal to V of T times I of T. Now, I have to be a little clear about this, because there's some ambiguity about the sign. When we're talking about power, if I have anything, and it doesn't matter what it is, if you have a voltage here, V of T, and a current I of T comes into it, then this is the instantaneous power associated with that element. And if it's positive, it's dissipating. If it's negative, it's supplying. Do you follow me, class? And by the way, over a cycle for either an inductor or a capacitor, at times you will be supplying power, and at times you will be actually taking power out, or be negative, or dissipating power. And here's why: because as over one cycle, all right, current's going to flow in a capacitor, charge is going to accumulate in the plates, a voltage is developed, an electric field is around there, electrostatic energy is left inside or in the area of that capacitor. Now, as the waveform starts going through the second part of the cycle, all that energy is dumped back into the circuit. So the net effect for a capacitor or inductor is it gets energy, then takes the energy and puts it back in the circuit. And the net amount of dissipation is zero. Follow me? Now, if you have a resistor, it dissipates power. But this is the instantaneous power, which means I have a current, I have a voltage here. If I take this voltage right here, if you ask me this, this is the answer. If I take this times this, I got 8.48 times 24, right? Then I have the cosine squared of 377t, or, wait a second, this should be 65 degrees, my bad. This is wrong, this is 65. It should be this times this, and I can use a trig identity and break up cosine A plus B times cosine A plus C, and I can break it up and I can reduce it, but essentially that's what you have. That current times that voltage is the power dissipated at any point in time. All right? Now the average value of power would be what? If I asked you I want the average amount of power dissipated in this circuit, what do you do, anyone? What dissipates power? That, right? How much power is dissipated by that element? 1/2 times the element's value of resistance 2, right? Times the peak value of current squared. What's the peak value of current squared? 8.48 squared. Follow me? That's all the power, average power dissipated, but it's not the instantaneous. Instantaneous would be voltage times current. That's it. That was something just to get you familiar with the differences. Any other questions? Yeah.
Can you explain for where is that 24 angle,
20 degrees? This 20 degrees is that 20 degrees. That 24 is the coefficient of that. Remember, when we talk about phasors, this is good for everybody. In engineering, you always do this. Give me 1 second. If I have a waveform in the time domain, Vm cosine of omega t plus a phase angle. In the phasor domain, that value, this is V of t. V of t is gotten from the real part of e to the j omega t times the phasor form of V. Now, the phasor form of V is equal to just Vm at an angle of 0 degrees. That's the phasor form. This is the time domain form. This is observable, it's something you can measure. This is not measurable. It's something we use to analyze circuits, all right? The relationship between this and this is just the real part of e to the j omega t times this, V phasor right there. Now the e to the j omega t breaks down as cosine of omega t plus j sine of omega t. Follow me? The real part of that is just the cosine waveform, and therefore you can see the only thing you care about is taking the magnitude of the cosine waveform and the angle, but it has to be in terms of a cosine of omega t. Yes?
2 pi is multiplied times pi. We have to convert to radians, sorry.
Say that again, sir? Well, see, up here is 65 degrees, right? That comes right in there, right? 8.48 is this, right?
He's asking how you got from 20 degrees to 65 degrees.
Well, if you take 2420 and divide by 2 minus j2, right? Isn't this really 2 minus j2 is equal to 2 times square root of 2 at an angle of minus 45 degrees, isn't it? Look, if I have 2 minus j2, isn't that 2 square root of 2 at an angle of minus 45 degrees? That's my question. Is it? Yeah, it is, right? I mean, we're engineers. We know this. So if I have that down here, and I take the angle upstairs, it becomes plus 45, correct? Plus 45 and 20 is 65. That's how you get it. That's how. Yeah.
Where does your 377 come from?
It's given in the problem. If you want to know the truth, I'll tell you exactly where it comes from. The wall circuit here is at 60 hertz. In radian frequency, it would be 2 pi times that, 120 pi radians per second, right? That's 377 radians per second. Yeah. Anybody else? Okay. Good. All right. Yeah.
Can you just repeat what you were saying about the positive and negative terminals of dissipation power?
Well, I'm saying that the way we define power, dissipation, hear me now, dissipation, That's gonna be a function of time, remember this. You take the current going into the positive terminal of the voltage. So this is the voltage V of t. Be the instantaneous power. But for a capacitor and for an inductor, sometimes it will be positive, sometimes it will be negative, and the net amount is 0 over a cycle. That's important. Okay? Anything else? Yeah.
What are the units of instantaneous power?
Watts. It's the same as any type of power is watts.
Okay.
It's always that. The average says it's average power. Instantaneous means it's an instant in time. And by the way, another thing I'm going to tell you guys, there's a lot of deceptive marketing and advertising you're going to run into in your life. And back in the day of when I was younger, high fidelity sound was the thing everybody wanted. They wanted the very best sound system. And they would advertise things deceptively and say it had 400 watts peak power. Well, they weren't talking about average power. They were talking about peak. That lasted for about 1/100th of the actual cycle that was being used, the frequency used to test it. The average power is like 40 watts, and they didn't even mention things like distortion. It's called intermodulation distortion. Hey, no quiz today. I don't need you. Go. Anyway, there'll be another one coming short. Anyway, the thing about it is, whenever you buy equipment and things like this, being engineers, look at the average power used, not the peak power. Remember that, because you're going to find all sorts of deception out there. There's one thing they like to do, is try to really fool you with their advertisements that they can still legally say are accurate. They're right, but it's wrong in terms of what they're doing. What?
Well, between the average and peak power, is there, what are the main factors that affect?
Average power, if we're talking about something out of the wall, what is the relationship between peak and average voltage, class? If peak voltage, or say if average voltage, RMS voltage, pardon me, is 117, what's the peak voltage? If RMS is 117, it's about 120 volts there, right? That's RMS. That's the effective voltage. What's the peak value? Square root of 2 times that. Follow me? So the peak value would be, you'd have to take 1.41 times 120 to get the peak value of voltage. That's the peak value of a waveform. Now for power, because of that, if you wanted the power, I'm just going to write this down. I was going to get to it in the lecture, but I'll answer it now. If we're talking about RMS values, then power in general, PAV, this is the average power associated with any circuit, but it's average. It's equal to either 1/2 I peak, or I magnitude, times V magnitude, or it's equal to, actually, let me do it this way. Let me answer this by going through something called power factor and going through it so I can do the entire portion of the lecture, not part of it. And that way it'll make a lot more sense. All right, this is something I want to make sure everybody understands. So if we have any, no quiz. If we have any element like this, all right, and we have some voltage V here, all right, I'm going to say this is V magnitude, or I'm going to use M for magnitude. That's equivalent to VRMS being equal to V magnitude over the square root of 2. Everybody got that? Now, actually, it's V magnitude, but let me go a step further. Let me say this is going to be V magnitude at some angle theta V. And so I'm going to go ahead, VRMS is V magnitude at some angle theta V divided by square root of 2. Can everybody follow me in this class? This is a relationship between peak, or magnitude of the voltage, and the RMS value of the voltage. This is assuming something is a steady state, something that's varying as cosine and sine. Everybody got that? So this would be like, if you wanted the actual one, it would be Vm cosine of omega t plus theta V would be the actual voltage here, V of t. Now, I'm just trying to tell you that's what we look at. Now here, there would be a current. This is going to be the peak current flowing in the phasor domain, not time domain. That peak current would be some Im, right? And here, it would be at some angle theta I. Follow me? Magnitude and angles, the only thing you care about if it's steady state. You get rid of the omega business, all right? Or, it would be the same thing as saying IRMS was equal to I magnitude over the square root of 2. That's I magnitude here, square root of 2, at an angle theta I. Now I've defined both voltage and current in terms of the magnitude angle and the actual, we don't have one. You're free to go. Anyway, it's magnitude divided by square root of 2 is equal to IRMS. Same angle, got it? Angle doesn't change. Now, the power absorbed by this is going to have a voltage across it, right? The power or associated with this is better. The power associated with that, and its average power, write this down, is equal to either V magnitude times I magnitude times the cosine of theta V minus theta I, or divided by 2, pardon me, divided by 2, or it's equal to VRMS times IRMS times the cosine of theta V minus theta I. If you look at the last lecture, same thing for PF. The last lecture, I went through and I took the instantaneous power and I broke it out into 2 pieces. One was 1/2 Vm Im times cosine of theta V minus theta I, plus, and then there was 1/2 Vm Im times cosine of 2 omega t plus theta V plus theta I. One was time varying, one was constant. This is the constant value, and it is the average power that's dissipated or associated with that element. It doesn't have to be dissipated, because if that's a source, this will be negative, and I'll get to that in a bit. Remember, current is entering the positive terminal. That's how our polarities are associated with. Current entering the positive terminal is dictated like this. Understand? If it was a source, current would be coming out, if you think about it that way. Source always supplies power. Anyway, that's what it is. Now, here's the thing you take from this. We don't write this all the time. What we do is talk about the power factor. Write this down. The power factor is equal to the cosine of theta V minus theta I. It's the relationship of the angular difference between the voltage and current. If it's a resistor, the difference between the theta V and theta I is 0. They are in phase, there's no difference. If it's an inductor or a capacitor, there's a 90-degree difference. And if you have a load that's a combination of a resistance plus an imaginary component, then the angle will be somewhere between minus 90 and plus 90, but you don't know what it is until you do the problem. Now hear me on this one, this is important. All right, if you can't read, just yell at me. This is cosine of theta V minus theta I. It's called the power factor. It's usually abbreviated just PF, all right? Now here's why this is important. Well, a couple things about this. You notice a cosine, if you have cosine of x, where x is anything, well, that's the same thing as cosine of minus x, isn't it? Cosine of what? Pi over 4 is the same thing as cosine of minus pi over 4. So there's something ambiguous about this. So they use the term lead and lag to actually identify what that angle is. And if theta V is ahead, is leading, well, yeah, I'll put it to you this way. Theta V minus theta I is greater than 0. This is going to be lagging. And I'll get to why it is. And if theta V minus theta I is less than 0, it's leading. Now I'll explain what I mean by that in a second. Whenever you talk about lead or lag in the power industry, the voltage is something that's almost always set by the power company. It's at 0 degrees. So if the current, it's always the current they talk about. If it's, say, if you've got a waveform cosine 117, cosine of 377t is the voltage in real time, measurable, and that's how we describe it on something. If the current is like 20 amps, cosine of 377t minus 30 degrees, that means the current is lagging behind the actual voltage by 30 degrees. Follow me? Therefore, if you have theta V minus theta I, that would be positive, and that means the current's lagging. Now I'm going to do problems to bring this out. Follow me on this? If the current is leading, if you have a voltage of, you can just put, say, 117 at 0 degrees, and the current is going to be 20 at an angle of 30 degrees, that means it would be leading the voltage by 30 degrees. So everything is relationship to where the current is with respect to the actual voltage angle. Stop. You know, that's not bad. I was in here when they were doing construction on ground topple and stuff like this. I mean, it was, this place was shaky. They had stuff going on there, and it got to be almost impossible to try to communicate. Were you guys, were you in here when we had all that construction? This place is a nightmare.
Yeah.
Oh, that's not bad. All right, now, so how do you use this? And here's what I'm gonna have. I'm gonna show you some things. Normally what they do is this. I wanna just get to the problems and show you how to do it. If I have time to get the complex power. So, why did I say what I did? I've gotta talk about a few other things too. When we talk about power, average power, P average. Remember, our average power, this is in watts or kilowatts, right? That's equal to VRMS times IRMS times the cosine of theta V minus theta I, or it's equal to VRMS times IRMS times the power factor. Please write this down. This is going to be important. You will get hurt if you don't understand this. Now, when I have that, the thing that is most valuable for you to do is see something applying it to a problem. So here's a typical problem. Typical. And almost all the stuff that you see in the power industry, and if you're mechanical engineers and aerospace engineers, I can almost guarantee everything they will be dealing with you with are going to be RMS voltages and average power. Right? For any type of energy conversion and things like that, that's what you're going to get. So if we have a source voltage Vs here, and we have some resistance, this may be a transmission line of a mile long, and it's going to have a certain resistance. Say this is 0.1 ohms. Then down here, the power company, by regulating, is going to have a voltage. One of the typical voltages that they deal with is 480 volts. In the United States, you're probably used to seeing the wall is 117 or 120, depending on how you read it. It's really 117 RMS. That's RMS voltage. And you will see the next thing you're going to get is a plus and minus that are 240 volts. If you have a dryer, anybody know what I'm talking about here? That's going to be a plus to minus, and then a minus to plus, but it's the same phase, and I'll get to that later. I'm sorry, I can't do anything about that thing. All right, so it's 240 is next. The next one doubles that, goes 480. Now, after 480, it can keep on doubling up to 7,200 volts. That's the voltage on the other side of the transformer that this branches off from. Remember that. Just one. Well, it's not critical, but if you think about a standard residential power supply, hey, look, I can't help it. What they have is a 7,200 volt line that's a single phase coming down to your residential neighborhood. All the transformers take that and step it down to plus and minus 117 or 120 volts. That 120 volt plus and minus 120 is what's feeding into your house. Now they have the minus 120 because for dryers and certain other things you need more power or more voltage usually to drive it. So that's the reason they have that. They could add a transformer, but it's easier to do it that way. How many are familiar with at least some of the things with electrical wiring in your house, right? Some of you are. Most of you have tampered with this in some way because you had to do something with a fuse box or something like that. All right, so that's the voltage. It's 480. That's by the power company. They set that thing up. They regulate. It's 480 there. Now, there's a certain amount of power that's dissipated. And if this is a typical problem. If they say the power used by this is gonna be equal to 88 kW, that's 88 kilowatts of power is being used by this. By the way, this is more of a non-residential. It's almost into, it's not quite there yet, but it's going towards an industrial type of application. So I've got, and it's at 60 hertz, but I've got a power dissipated there of 88 kilowatts. Now I want to know what the voltage is back here at the actual source point. So that would be a voltage downline that is being, this is regulated, but this is something we've got to calculate. That's force to 480. Don't worry about why or how. That's 40 volts. Here's how we do it. I know what I really need is the current, don't I? Because if I have that current, I can get that voltage. Do y'all agree with me? Now, the 480 here is always assumed at 0 degrees, unless stated otherwise. You always assume this is the line voltage, just like the 117 there, or 120, would be assumed at 0 degrees, unless somebody would blatantly say that it wasn't. That's considered the reference voltage. Now, when I have that, I want this current, and this is RMS current. So I want the RMS current. This is RMS voltage, by the way. That's VRMS. They always use RMS for power applications. So now I come over to here, and I said, well, I know what the power is dissipated. It's 88. Follow me, class? 88 kW. So I have 88 times 10 to the third watts is equal to VRMS is 480. Please watch this. 480. Now it's times IRMS. And there's going to be a power factor here of, in this one, it's 0.707 and it's lagging. And write the word lag. That means the current is going to be behind the actual voltage. Now the voltage is at 0 degrees. The current's going to have a negative angle associated with it. You follow me, class? Please watch this. So now I have to calculate that current, IRMS current. So it's going to be 480 times this times the power factor of 0.707. And that means my current, my RMS current that flows is going to be 88 times 10 to the third over 0.707 times 480. And that will be my value of IRMS. Somebody give that to me. This is the magnitude. I'm going to show you the angle in 1 second.
259.3.
259.3? I believe that's right. Now, the angle we get by coming over here. And I said the power factor was 0.707 lagging. Well, the cosine of an angle equals 0.707, or 1 over the square root of 2 is 45 degrees. Do you all know that? I chose that one for a reason, because it's obvious to most of us. But it's lagging, which means the current is actually going to be at minus 45 degrees. Does everybody see that? Now I have the current in the circuit, right? I have the voltage across the load at 480. If I want the voltage Vs here, I can say that Vs will be equal to, think about this. I've got the current through here, right? So it'd be 0.1, right? Times IRMS that I've got right there, plus 480. And that will give me the voltage of the source. Calculate that for a second, if you don't mind. Just 0.1. Now remember this though, I didn't say this loud enough. That I is at an angle of minus 45 degrees, so it's a polar number you have to. It's going to be 0.1 times this at an angle of minus 45 degrees plus 480. And what do you get for that? That I can't do in my head. Anybody? Remember, it's polar, right? Here's the problem. A lot of people just say, oh, that's 25.93 plus 480. No, it isn't. That's at 45 degrees. Right? It's got a real part and an imaginary component to it. What do you get for this? And give me magnitude and angle, please. Bring your calculators.
49.67, angle of negative 2.1.
Say that again.
49.
No, man. This is 480 here. It's,
49.
What?
489.
489. I'm sorry.
Yeah, sorry.
I got deaf.
No, it is.
489 at an angle of. Say it again.
Angle of negative 2.1. And that 89 is 98, my bad. It should be 498.
All right. Almost 500. That's fine. It's almost 500 volts, right? Our line voltage is 480, but we need 500 to get there. Now, yeah.
Where, I know you said I spaced out, what was the negative 45, where did that come from?
It says, I said that the power factor is lagging and it's 0.707. Lagging means the angle will be negative associated with the current if the angle of the voltage is 0 degrees. This is almost always the way it's done. Follow me? Just let me finish this. I know we got a test coming in here next, but if that's the case, that's the voltage. Now listen to me carefully. What power companies do is incentivize, not your residential areas, but any kind of industrial complex that uses a lot of power. If you don't have a power factor below 0.9 or 0.95, they start fining you. And here's why. Let me show you. What happens if the power factor here is not 0.707, but it's perfect, it's 1. All right? If the cosine of theta v minus theta I is 1, that means the difference, theta v to theta I, is 0 degrees. Do you agree with me? Correct? All right, if this is the case, and it's still 88 kilowatts, then over here, we go to 1, right? And if that's 1, what happens to the actual current? Class, just calculate it for me.
It dips by a lot.
Just take 88 times 10 to the third divided by 480. Anybody? Help me out. 183? 183.3 at an angle of 0 degrees, right? All right, now our new voltage, instead of being 498, the voltage at the source would be 0.1 times that, 183 at an angle of 0 degrees, plus 480. What do you get for that? Anybody? No. Well,
498.33.
I'm questioning this. Is this right?
That's what I got.
All right, and what do you get for this one?
It only reduced by 0.32
498.3.
at an angle of
All right.
0.
The thing about this is how much less is the current? It went from 253, right, down to 183. Now, if you think about the power supply, voltage times current, right, the power, the amount of current here, 183 will have a lot less losses in the line than 253, or whatever it was, follow me? Because the lower the amount of current that is required to get the same power, the better it is. And that's why industries will fine you if your power factor is above a certain level. And they measure this. I mean, I don't know all the laws, but I know that if you have, in major industries, power factor is super, super important, and they have ways of taking care of it. All right, guys. I'll give you some more homework. See you on Monday.